Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on December 17, 2025, about 9 days ago. This paper introduces Spatia, which keeps a persistent three-dimensional scene point cloud as updatable spatial memory, so video generation stays spatially consistent over long horizons, while still allowing realistic motion. The paper is titled, Spatia, Video Generation with Updatable Spatial Memory. And as we'll see later, that simple idea of rendering and updating a scene memory unlocks some really practical camera control and editing behaviors. Also, the authors shared a GitHub repo for Spatia. You will find a project overview and method description, plus assets used in the project. The repo centers on long horizon, spatially consistent video generation with a persistent 3D point cloud memory and SLAM-based updates, and it links out to the project site. Figure 1 explains why Spatia stays coherent over time, because it keeps a three-dimensional scene point cloud as a persistent memory that gets updated after each generated clip. The full diagram lays out an iterative loop from an initial image to a point cloud, then clip generation, then memory update. Panel A highlights dynamic static disentanglement, meaning the point cloud stores the static room while moving people are generated separately. Panel C and Panel D show camera paths and direct scene edits. Figure 2 shows how training teaches the model to use a persistent three-dimensional point cloud as spatial memory, so generated clips stay geometrically consistent. The full figure lays out the whole training pipeline. Panel A estimates a scene point cloud from one candidate frame, then renders that point cloud from the camera views of target and preceding frames. Panel B retrieves reference frames using intersection over union, which is a simple overlap score that keeps only spatially matching views. Panel C feeds point cloud renderings and references through a variational autoencoder, encoder, and control net into a multimodal diffusion transformer. Table 2 shows that the spatial memory approach produces videos that match real ground truth footage more closely on the real estate benchmark. The table reports peak signal to noise ratio and structural similarity, where higher means closer to the reference video, plus learned perceptual image patch similarity, where lower means more perceptually similar. Spatia leads the list on all three metrics, which suggests the point cloud memory helps preserve scene structure during generation. Table 6 means the explicit memory keeps long videos coherent, instead of drifting as generation continues. The full table compares WAN 2.2 against Spatia across 2, 4, and 6 clips. WAN 2.2 drops in camera control and in PSNRC as clips increase, which signals growing spatial inconsistency. Spatia stays near 84 on camera control and keeps PSNRC around 18 to 19, while LPIPSC stays much lower. Alright, two takeaways stand out. Spatia gets long horizon coherence by storing the static world in an updatable three-dimensional point cloud, and it still generates lively motion by keeping dynamic entities separate. The broader implication is that explicit geometry can turn video generators into controllable, editable systems, not just one-shot samplers. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.